Good morning, everyone. My name is Pierre Krieger, also known as Tomaka on GitHub and on Twitter. And this is not my laptop. I'm sick. I hope I'm not going to lose my voice, so everything is cool. If you check my GitHub, I have a bunch of game dev-related libraries and graphics programming-related libraries. But I'm not going to talk about game dev or graphics programming at all today. I'm going to talk about peer-to-peer networking, and more specifically Libp2p, which is a peer-to-peer library written in Rust to write peer-to-peer networks. And you can find the link on GitHub there. So before diving into Libp2p, I'm going to explain how a peer-to-peer network works. So I am going to assume that most of you know what a peer-to-peer network is already, instead of having a central server where everyone connects to. All the clients of the network directly connect to each other, which is better for a lot of stuff, for a lot of reasons. I'm not going to elaborate. You probably know BitTorrent, Bitcoin, IPFS maybe, I2P maybe, I'm not sure. Check them out on Google. And so, how does a peer-to-peer network work? It's made of 4 components. First, each node, each machine that connects to the network is identified by its public key, its cryptographic public key. And I'm going to elaborate afterwards. Second component, you need some system to discover how to connect to the network. Third component, you need a messages system, a publish-subscribe system, in order to propagate events on the network. And fourth component, a distributed hash table if you want to actually store values. But you don't necessarily need an event system or a DHT. These are optional, but you need one of the two, otherwise your system is quite useless. So first of all, public keys. That's what defines the identity of a node. It's, as I say, is identity. There's no other way of identifying someone. Everyone is anonymous except for their public key. So in Libp2p, a public key is represented by a string like that, QA, QMUTAH, etc., etc. And the format of this is basically the hash of a small data structure containing a public key, which can be RSA, ED25519, or SecP, or any asymmetric encryption that exists. It's designed to be very extensible in Libp2p. And this is strictly enforced so that you cannot spoof, you cannot steal someone's identity. You need to prove that you are the owner of a public key when someone connects to you. And the fact that this is the identity of a node makes it possible to build a reputation system on this. Just like on a public forum, imagine you register to a forum, you choose a nickname, and then you post, you become popular, etc., and people gain trust in you. We do the same in peer-to-peer system. You generate your public key, and then you participate in your network, and you build trust and reputation. And you get more trustworthy, and that's how we usually build more complicated systems. Sorry. I said I was sick, so I'm going to cough a lot, and I apologize in advance. Second component in a peer-to-peer system is the peer discovery mechanism. So imagine you create a network, you want people to connect to it, but how does that work? People need to know, your program needs to know how to connect to a network. And we have various ways to do that. You can, first of all, discover the nodes that are on the same network as you. And to do that, we use MDNS or DNS-SD. So the way this works is you just broadcast a message over UDP on the UDP multicast IP. And every node on the network receives this message and broadcasts the IP, and so nodes just discover each other and connect to each other. That's how you do on a local network. You cannot do that on the internet, because you cannot just broadcast a message on the entire internet. That's not going to work. So to do that, to connect to a network on the internet, we need bootstrap nodes, which are an IP address which we hard code inside the program, and the program just connects to them. You're going to say that's pretty centralized. We need to hard code IP addresses in a program, but we have no other choice, unfortunately. So that's a hack, but we have no other way right now. And that's the first step. That's what gets you on the network. But once you are connected, you can just broadcast messages to the nodes you are connected to and share information about the network, information about the topology. You discover the rest of the network, and then you build your whole network, and you connect to thousands of other peers. Once you are connected, third element, you can start broadcasting messages. So why do you want to broadcast messages? For example, in a chat application, imagine your network is just simple chatting. Every time you type a message, you broadcast it to everyone. That's the first example. Second example, in blockchain technologies, if you are familiar with how blockchain works, whenever you generate a new transaction or a new block, you also broadcast it to the entire network so that everyone knows about this transaction or block. Or, as I just explained, once you are connected, you just spread information about what you know on the network so that nodes discover each other. And events typically include a topic so that we don't flood nodes that are not interested in something with garbage. And fourth element, a hash table. So if you are familiar with IPFS, IPFS is a way of distributing data. And IPFS is based on a hash table, and more specifically on Cademia, which is the most popular algorithm for hash tables. And what is a hash table? It's basically the same as a hash map in Rust, which associates keys with values, just a key value store. Each key has an associated value. The difference is that in a distributed hash table, as its name says, it's distributed, which means that each node only stores a partial view of the hash table. So, and to determine which value you store, you don't store everything, you only store a partial set. To determine which values you store, you use your public key, which I explained 3 slides ago. You store up to 20 values, and to do that, use the distance between your public key and the key to store. So you store up to 20 values, which have 1 bit of difference between your peer ID and the key you store, plus up to 20 values whose key is 2 bits away from your peer ID, and so on and so forth. Which means that in order to determine where to find a value, you find the nodes whose public key is close to the value, and you just ask these nodes for the public key. The drawback of a DHT is that it's quite easy to attack, unfortunately. This whole system assumes that the whole network is not malicious, that everyone plays the game. And there's a lot of research being done about how to make this more robust, but right now we have no solution. And yeah, that's also a hack. We are researching how to do that better. And I showed a little diagram underneath to explain. So this, the colors are not great, but for example, in a DHT, this node only stores these 2 values, this node only stores these 2, and same for the others. And you just query the node for which value you want based on its peer ID. And after this brief explanation, I'm going to introduce Libp2p. Libp2p is basically something that does all what I explained automatically. So what Libp2p is a framework library designed by a company named Protocol Labs. That's the company that managed the specifications, that's the people who created it initially, and they are designing it as well. You can find more information on libp2p.io. The origin of Libp2p is that it was the networking system of IPFS. And IPFS uses Go and JS implementations, which were initially part of IPFS and were extracted into their own thing, named Libp2p. What we've been doing at Parity is write the Rust implementation, and that's what I'm presenting today. You can find the link on GitHub there. We started this 1 year ago, approximately, in October, I think. And it's almost ready to be published. We are going to publish version 0.1 next year, but it's like a polished version. It's not like a first draft that we just quickly publish. It's something that's supposed to actually work. If it doesn't, please file issues, but only beginning of next year. It uses Tokio. We want it to be as fast as possible. We want it to be asynchronous. We want it to be possible to have hundreds of nodes connected to your machine without any performance issue, hopefully. And we're using it already at Parity in what we call it Substrate and Polkadot. I don't know if you heard of Substrate and Polkadot. They are blockchain technologies. And Libp2p is the networking system of Substrate and Polkadot. And you can see it in action at telemetry.polkadot.io. If you type that on your laptop, you can just see it in action. You have a list of nodes on telemetry. Oh, maybe I should show this, whatever. You have a list of nodes. You just see we have approximately 70 nodes in Polkadot right now, which is not a lot. But you can just try it out and see how much we can grow the network without it crashing. And we are betting on Libp2p because a lot of people are actually betting on Libp2p. Ethereum 2.0 is probably going to use Libp2p, and that triggered the chain reaction. A lot of people who are in the Ethereum ecosystem are also going to bet on Libp2p because of that. It's like a really growing thing. And the good point about everyone betting on Libp2p is that we can actually share a network so that you don't have hundreds of different peer-to-peer networks. We can all have one network, which then discovers sub-networks. And that's the advantage of having lots of people bet on Libp2p. And before going further, I invite you, if you have your laptop on you, you can try it out now. I would be pleased if some of you did by typing this command, cargo install. I hope you trust me to not have put a malicious piece of code in there, but if your laptop starts crashing or something, you can find me afterwards and beat me down. So if you want to try it out, type cargo install with this git URL and then run it with rustrush-demo. How do I add stuff? Oops. That's not my laptop, sorry. Oops. I'm Tomaka, and I'm going to wait for you to type things. So the way this demo works is it's going to find people on the local network using MDNS. So I'm connected to the Novotel lobby Wi-Fi, but I expect it to not work properly, MDNS here necessarily. So I also created a bootstrap node on a server. So it should just work if you launch the demo. Everyone should be able to connect to each other. That's not decentralized since I created a bootstrap node, but that's a workaround because I don't think the Wi-Fi here is reliable. And also many people are on different Wi-Fi. So if you connect, you should be able to chat. You should see my message. And I'm going to go back to this demo afterwards. So it uses MDMS to discover local nodes. It also uses a bootstrap node. And every single node it discovers, it tries to connect to, and it tries to maintain a connection to. And whenever you type a message on the chat, it just broadcasts the chat message everywhere, so everyone receives the message. Of course, you have no history. If you connect, you don't see what people have typed before you. You also, the UX is not so great. And you can, of course, check out the source code, but keep in mind that we are trying to improve the API, and the source code is quite messy right now. But you can check it out. And piece of warning, we haven't tested Rust Libp2p with more than approximately 80 nodes. So you might find a bug, but hopefully not. So I'm going to continue. I hope everyone saw the URL. So let's dive a bit more into Libp2p. The special things about Libp2p is that it's very modular. So we're not using just an IP address on a port. We're using what we call a multi-address. Instead of having just an IP address on a port, we have a string IP4 / your IP address / TCP / your port. And the advantage of this is that we can basically do anything we want because we just have a string. So instead of using TCP, you can use UDP. You can use QUIC on top of UDP. You can use IPv6. You can use WebSockets. The third example has a /WS, which means put WebSockets on top of this TCP connection. And why do we want WebSockets, are you going to ask? Because browsers can only use WebSockets. And a use case of Libp2p is we want it to run inside of a browser. And it works right now. You can compile Libp2p and run it in a browser and connect to other nodes, which is quite nice, I think. So right now, Rust Libp2p supports TCP, WebSockets, DNS. You can put a DNS domain name. And Unix domain sockets, that's obviously disabled by default because you don't want to tell another node to connect to its local socket. That's not very secure, but it's supported. In the future, we want very much QUIC, which is the protocol designed by Google on top of UDP. That's basically a replacement for TCP/IP. And Bluetooth as well to create a true mesh network where people are connected to each other locally. And Tor for more privacy. That's for the future. Here is an overview of the protocol on the wire. So what happens when two nodes connect? So they use a transport, a multi-address, to decide how to connect to each other. TCP/IP, WebSocket, what I just explained. Then once they connect, they negotiate an encryption protocol to make sure that their peer ID is correct. On top of this encryption layer, we're using a multiplexing protocol so that you can divide your connection into multiple substreams, as you can see on the schema. And then once you negotiated this, you can open as many requests as you want. Each request is a different substream, and they are all grouped together with a multiplexing protocol. Right now for encryption, we are using a protocol named Tokio, which is basically the same as TLS, but without certificates. You're going to say, don't roll your own crypto, and I agree with that, which is why we're going to switch to TLS in the future. For multiplexing, we're using Yamux, which is made by Google, if I'm not mistaken. But we're going to switch to QUIC eventually for both the multiplexing and the encryption. And as I said, one of the strong points of Libp2p is that it's modular. That's actually a very important point. So even though Protocol Labs is designing the thing, the only important part is the core of Libp2p. On top of that, you can just design your own protocol. You can do whatever you want. Once you have encryption and multiplexing, you can just create whatever protocol you want on top of that. Libp2p doesn't assume that any protocol is supported. You can just pass any protocol name, and if a remote supports the protocol, it's going to accept and start speaking the protocol. So you can just create your own network with whatever protocol you want. And this is really cool. Even if you know in advance which protocol you support, it's still pretty nice to be able to experiment with new stuff. Imagine you want to replace a protocol with another. You create your new protocol, you add support for both, and then you remove the deprecated one live without having to do a breaking change. And that's it. I'm going to switch back to the demo. OK, we have 2 people, including me. Are more people on the demo? If something's not working, please tell me. So, oh yeah, OK. Just compiling. Yeah. OK. So that's it. Thank you. If you have questions. And Parity is recruiting.
Yeah, we have some time for questions. So, anyone?
Hi, thanks for the talk. I have a question. What about attacks to DHT? Does it have some protection against the DHT poisoning, maybe Sibyl attacks or something like that?
We don't have any protection against poisoning, unfortunately. We actually had, so we're using Libp2p in Substrate right now, and IPFS also uses Libp2p. And to give you an example, the DHTs accidentally merged once, which means that Substrate got polluted by IPFS, and IPFS got polluted by Substrate. And that was really nasty because Substrate just stopped working because of that. It's basically an attack, but involuntary. And we don't know how to fix that yet. Like, it's ongoing research. Like, Protocol Labs is actively researching how to fix that.
Maybe another question. Does it implement something for NAT traversal, NAT traversal?
NAT traversal. So I have a bonus slide. I kind of anticipated this. So right now, all we do is whenever you connect to the network, whenever you dial a node, you ask which IP address is yours, which gives you your external IP address, and then you advertise this IP to a network. That's all we do right now. In the future, we're going to do UPnP, but that's actually not working in practice. That's working in theory, but in practice, UPnP is very crap. PCP also is not working very well, so we haven't prioritized this very well. The solution we have is relaying connections. So the way it works, you just ask another node to relay everything you do through it. And if you need a direct connection to a node, you use this relay. In practice, you probably don't really need a lot of NAT traversal because you just broadcast messages usually. And so you don't really need a direct connection to a node. A node behind a NAT just dials someone and then broadcasts message to this peer, and that's it. NAT traversal is quite important for the browser use case because browsers are like behind a virtual NAT more or less. Like the browser doesn't allow any incoming connection, so that's very important. But that's all we do, relaying connection and discovering new external IP.
Other questions? Okay.
Thank you. And does Libp2p has the ability to pin some key and value, like in IPFS, never purge this data from the node storage?
Sorry, what's the second part? Ping a value?
I want to keep some file always store it on my node and never purge it from the storage.
So Libp2p doesn't do that directly. That would be on top of Libp2p. We're just doing the networking, but we expose everything you need to do whatever you want. The API should be very flexible. So if you want to keep your value in store, you just do it manually. Like, Libp2p is not going to decide which values to purge or to store or blah, blah, blah. That's your program on top of it.
Okay, thank you.
Maybe?
So I have several questions. So first one, does Libp2p has a reference, or is it a reference implementation which is not compatible with JS and Go implementations? Second question is about comparison with noise protocol. So
with what, sorry?
Noise.
Oh, noise.
Yes. Okay, I had a third question, but I forgot it.
The first question is the reference implementations. So there's the history of Libp2p is that it was initially part of IPFS, and then it was split. So the reference implementation is this. It's the JavaScript implementation, actually. And ProtoGlabs is currently writing a specifications, which we are trying to follow, but it's not complete. It's an ongoing effort. They are recruiting a ton of people. They are recruiting technical writers to write an actual specifications. The reference implementation is in JavaScript right now, and we're trying to follow it as much as possible. But since it's code and code is messy, we're not sure we are compatible, but we are trying to be. And as for the noise protocol, I don't know, actually. I'm not the one who designed this. I know, so we have someone named Jeff at the Web3 Foundation, which is friends with Parity, who has been looking into this, who opened a few issues, I think. So someone is looking into that, but not me personally. So.
And if I understand correctly, Libp2p doesn't have any protection against man-in-the-middle attack, because we don't use public key as identifier of a node.
Well, it's all the communications are encrypted, so you are protected. So you know in advance the peer ID of the node you're supposed to connect to, and when you connect to, you verify its identity. So there should be no man-in-the-middle attack possible. Well, I don't see what you mean.
So we don't have any central authority, right, which can identify nodes. We don't have, well, like in web, authority centers. So this is why man in the middle can impersonate other node if we can interfere with the traffic.
The equivalents of the central authorities are the bootstrap nodes that you hard code in your program. These are like the certificate authorities, more or less.
So bootstrap nodes provide us with public keys of other nodes.
Yes.
Okay.
Yeah.
Thank you.
Okay. Next question.
Thank you for the talk. And my question is, did you ever did some kind of measurements, benchmarking for the throughput of the network or like bandwidth?
Unfortunately, no. So the closest thing I have to benchmarking, I wrote a small, how to say that, basically a test. I'm spawning 25 nodes, and they all talk to each other, say hello world to each other. And that takes, I think, 30 seconds or so to spawn 25 nodes, and they flood each other, and I don't remember how much data, which is honestly quite bad, but we want to improve that, but we haven't done that yet. We have taken over possible decisions to make it fast. So what I mean is that the design is made to be fast, and now making it actually fast is just a matter of measuring and fixing things that are slow, like unnecessary allocations and so on and so forth. If you see what I mean, like the design is made to be fast.
Okay, and is there any kind of limitations inside the protocol itself? The way it does encrypt, the way it does like broadcast messages and stuff like that?
Sorry, what's the question?
So, is there any kind of limitations included in the protocol itself? The way it encodes the data, decrypts the data, encrypts the data, stuff like that?
A reference?
No, just well, you. I think you know the protocol better than me.
Yeah. Well, I don't know.
That's so. That's the question is there any kind of limitations in the protocol itself? So maybe there's.
I'm sorry, I just don't understand the word you say.
Okay.
What
that doesn't matter. Okay, thank you.
I'll try to clarify maybe. Not like are there limitations not in the implementation, but in the protocol, like in theory?
What? I don't understand the word. What?
Limitations.
An implementation?
Limitation. Like limits.
Oh, limits. So right now, more or less, like there's the negotiation protocol is badly designed, and we are actually not following the design in order to make it actually fast. but they are fixing this. There's like, you cannot just assume that negotiation is succeeding, so you have an extra round trip, and that's, thank you, whoever did that. You can not just assume that negotiation is succeeding, but we are fixing that. Other than that, there's no limitation in the design.
Thank you. Any more questions? Or should we let Pierre on stage?
And what about protection against deep packets inspection? Is it possible to distinguish Libp2p packets from other packets and block them?
Well, you can for sure determine if a connection uses Libp2p. If we're going to implement Tor and maybe I2P, maybe that will fix this. But other than that, no, you can pretty easily know that a connection uses Libp2p, unless you use WebSockets, and since it's encrypted inside WebSockets, you cannot tell.